today. Last time we discussed about the separation of variables using this technique to solve the Laplace equation. So what we did before was to simply assume that the v of x, y could be written down as a product of vx times vy. And in this case, the Laplace equation can be actually separated out into two parts. So the first part only contains expressions of v of x, and the second part only contains the expression of v of y. And now, since the two terms are completely separated, we can deal with them separately. And so say that we assign the first term as a positive constant, so we represent that by a k squared, and the second term as a negative constant, that is minus k squared, then this function Laplace equation is satisfied. Now here, without loss of generality, k is a positive number, and because what really matters is k squared. And you might ask that it's also possible that the k square, there put an additional minus sign here and remove the minus sign there, and that's another possibility. So really, what the final expression can be written in terms of either the form in above and or the form in below. So both are supposedly possible solutions without considering about the boundary condition. Now let's see what the boundary condition plays the role, and how it will help us determine the coefficients. So if we apply the first boundary condition, so there are four boundary conditions. There are two boundary conditions. That's the this one is at the xy plane, where this one is at xz plane, where the y is 0, and another is this plane of y equals a. So at these two planes, the potential should be 0. And the third condition is at the yz plane, the b should be as a function of y. And the last condition is simply as you go to infinity, the potential should be 0. Now let's apply the first boundary condition. Say that when v equals 0, y must be 0. When y equals 0, v must be 0, which means that let's plug in the y equals 0. So this term is 0, but if y is 0, this term is a constant. So this means that if this boundary condition to be satisfied, we must have d equals 0. Or we can simply cancel this term out. And on the other hand, this term and this term cannot satisfy, because this two always has a finite number. This means that even though here the second expression can exist possibly if we didn't specify the boundary condition, but the boundary condition here, the first boundary condition actually killed off the expression here, because here e must be 0 and f must be 0, then the entire expression is 0. So this kind of solution does not exist, and what's possible is only the first kind of expression. Now let's take a look at when y equals a, we also need to be 0. So when y equals a, so here the sign must take a 0. This means that this ka must be integer times pi, because sine n pi should be 0, and this means k should actually be n pi over a, where n can be any integer. It can be starting from 0 or 1, 2, but say that if we plug in 0, then this is simply a sine 0. Sine 0 is a 0, so the Vxy is again a 0. So the k equals 0 doesn't mean too much. So in reality, the k should actually start from 1, 2, 3, and is a positive integer. Now, let's take a look at the fourth boundary condition first. Here it's saying that as v goes to 0, as the x goes to infinity, the v must be approaching 0. And if we look at the two exponential functions, the first exponential function is exponentially growing, while the second one is exponentially decaying. So this last boundary condition eliminates the first expression, and what's left over is only constant b and c. And then the only boundary condition left over is also the third one. This means that here, if we simply absorb b and c, two constants, into a single one, then here the Vxy should be written as this constant times the exponentially decay function in the x direction and the sinusoidal sine in the y direction. And here, remember that the k only takes certain values. And the next thing that you must be aware is that because this Vn is a solution to the Laplace equation, any linear combination of Vn is also a solution to the Laplace equation. You can see that here, if you take the Laplace operator on v1 plus v2 is simply Laplace operator operating on v1 only and operating on v2 only. And if this one is 0 and the second one is 0, then the final result should be also 0. Then this means that now I can simply write this as a sum over all these possible solutions. And if I re-express this, if I evaluate the potential at x0, that means we plug in x equals 0 here, so this exponential is a constant 1. And now this is the expression at the boundary x equals 0. And at this boundary, the v should be a function of vy. If that's the case, then this solves our problem, because the final boundary condition is v equals vy at x equals 0. Now, let's check if we can solve for this Cn. So the trick to solve the Cn is the following. So we can first add an additional sine n prime pi y over a and integrate over y. So that is now we added this additional integral from 0 to a. And we copy down this n pi y over a first, and we want to add additional term. So this doesn't change the expression, except that the left and the right hand side are both multiplied by this sine n prime pi y over a, and do the additional integral from 0 to a. Now let's take an additional look at the expression over here. So this expression is special in the sense that the sine n pi y over a is the sine Fourier sine series. And if you look at the video that in the homework 1, you may realize that this is related to the Fourier analysis, and it simply maps from one positional domain to the frequency domain. And the sine n pi y has a very special property that if you do this integral is simply 0 if this n is not equal to n prime, and this integral is a over 2 if n equals n prime. Naively, you can you can try to work this out at home, but this means that the sine n pi y this series of functions are orthogonal to each other, because this the integral of 0 to a and the sine 1 and sine n prime can be a sort of inner product between the two functions, and the first one is saying that the two functions are really orthogonal to each other, and the second one is saying that the sine n pi y itself, what the normalization factor is. So here a over 2 is simply the normalization factor of this sine function. Now keep this in mind, then we can actually calculate the result of this expression. So because this n only equals n prime, and this one takes a finite value, then this means that the sum here is only non-zero at n equals n prime, which means here is Cn prime so the second term is a over 2 already, and equals to so you can see that somehow by rewriting this expression in terms of n prime, the Cn is actually out of the integral, and so what you need to do is you only need to rearrange the terms, and that simply gives you the expression for Cn prime. And because here n prime is really a dummy index, so I can erase this n prime and write this as a dummy index n. Now this means using this trick, we actually obtain the C for any index n. This means actually that is already the solution to the problem that we are trying to solve. So the the function of x and y should be really expressed as the coefficient Cn, where Cn is given down below here, and then on the x direction it's an exponential decaying function, and on the y direction it's a sine function. And now we can further evaluate this integral if we specify this v0 and y. So say let's set this v0 as y as a constant of v0. Say this means that Now we can evaluate this Cn. The integral on the right simply gives let me see. If you finish this integration at home, you will realize that the Cn is actually 0 if n is even, and it's 4 pi naught over n pi, 4 v naught over n pi, and if n is odd, and now let's write out the expression of the Vxy explicitly. Then the final expression is simply changing the Cn into a function of 1 over n, and summing over all of this odd n index. And somehow this expression can be summed together. And if you are interested, you can try that. And now you can see that really starting from the separation of variables, we first think that the v of x and y could be written as a sum over all these possible solutions, and then using this Fourier transformation, we are able to determine the Cn coefficient, and finally we obtain the solution of Vxy, and for this when v of y is constant, and you can double check that this solution is indeed satisfies the Laplace equation with the correct boundary condition. And but this sounds too good to be true, right? So how is that possible that somehow all these solutions is really all the solutions that's needed, and is it possible that you are missing some of this basis or some of this potential solution to the problem? So say that if you miss a term, then you cannot sum them together to find out the final expression here. So here we didn't miss a term because that it is guaranteed by this the completeness of this Fourier series. So you can prove that actually the Fourier series functions are orthogonal to each other, and they form a complete basis. What I mean is that the sine n pi over a functions, if you count n from 1, 2, 3 to all the integers, they form a basis, and any function can be expanded in this basis. So here, as the example, I'm trying to expand the constant over all the basis functions. And here, when n equals 1, is simply trying to use sine x sine pi over a to approximate this constant. Of course, the two differ by a lot. And now you can see as I add 5 more bases, that is because only the odd functions are considered here. And then you can see that that is the orange line. The orange line, even though it's still not a constant, is starting to approach the constant. And as you add even more terms, that is about 50 terms, and you can see the green line is really already close to a constant, except at the two edges. And as you have 500 of them, you see that's the red one. So the red one is almost a flat line here in the bulk, and there is a sharp change at the end. And this, if you include this n up to infinity, then the difference of the two are almost zero. And this completeness is not easy to prove, and that is what the mathematicians told us. And it's a very complicated problem to really prove that all these functions are really a complete basis. And now if we take that as granted, then this means here all of this basis is really the complete set of the possible solutions. And as long as this v of y is any function that you specify on the boundaries, as long as you specify that, you can always find out the Cn index. And if you match this Cn index by calculating the overlap of the basis functions, then you can get this Cn, and as you sum them all together, you will recover the boundary condition. And once you recover the boundary condition, this v of x of y is already a solution of the Laplace equation in the bulk. So here this trick, by integrating over 0 to a in the order this in the region of interest, and adding additional sine n prime pi y over a term. This is a trick that helps you to calculate this Cn index. And you can think of this as by projecting this original v of y onto this sine n pi y basis. So that is my understanding. So say it another way is that we are trying to express v of y in terms of all this sine n pi of y of a, and this Cn is really the overlap between this vy in terms of all the spaces. And to get this Cn basis, we simply do an integral of vy and sine n pi y over a, while keeping in mind that the sine n pi y over a is not normalized, like the normalization factor is a over 2. And this Cn is really the overlap of the vy and the sine n pi y with the normalization factor considered. And the technique to determine the Cn is shown over here. Okay, then in the next we will try to use this technique. So first write down the complete set. That is first write down the result like as a function like this, where the Cn are coefficients that are unknown to us, and then we try to determine what the Cn is by the boundary conditions. And so this is the problem in 2D Cartesian coordinates, and next we will apply the same technique to 3D Cartesian coordinates and the 3D spherical coordinates, And in the homework, you will be doing the problem in cylindrical coordinates as well. Okay, so any questions about this? Okay, you might need to think about this again because it looks easy, but it may actually not be quite as easy as you thought. And as you go through some homework problems, you might find out more. Okay, I'm finished this part now. So let's take another example. So in the previous example, it's v equals 0 at the top and the bottom, and v is the constant on one edge, and however it's an open box on the other end. Now I try to seal the other end with negative v naught, and see what happens. So now this means that again there is no z dependence on this problem. So the problem is 2D again, which means it's now let's look at the boundary condition. So the boundary can be so the v equals 0 when y is 0, and v equals 0 when y is a, and on the left edge when v equals minus 0, when x equals minus b, and v should be a constant v naught when this x equals b. So these are the 4 boundary conditions. And we already know that the solution, according to our previous separation variable calculation, we can immediately write down the solution, right? Say this, and that's what I just copied from the first example. Now let's check about the boundary conditions. So here it says that v equals 0 when y is 0. So let's check y is 0. So here this term must vanish. And then the second term is v equals 0 when y equals a. So here when y equals a, the sign k a should be 0, which means Ka must be n pi. And now here the boundary on the x-axis is slightly different from previous. So here the v must be minus v naught when x equals minus b, and the v equals v naught when x equals b. And here this means that Now if we let me see. If we then if we take a look at this expression and another way to express, so in principle from the two expressions you can get a you can determine the coefficient of a and b in terms of the v naught, but let's try another way, is that we actually realize that this here this function a plus b a exponential plus b exponential should be an odd function. So because here this v should be a minus v when x equals b minus b, and v equals b v naught when x equals b, and then we can rearrange this exponential functions in terms of sinh function and cosine functions. So this is hyperbolic sine and hyperbolic cosine functions, and so hyperbolic sine functions are really I simply here call it sinh. It's and the cosh function is the hyperbolic cosine function, and this is the average of decaying exponential and increasing exponential. So this cosh function is an even function, and this sinh function itself is an odd function. So this means that if we re-express this sine functions, this exponential functions in terms of sinh and cosine, this boundary condition here really says that the b prime here should be 0, and what's left over should be only a prime. So now let's rewrite the results. The result should be again a constant. So this expression is slightly different. But if you compare the expressions above, you can see that they share the same spirit. So previously it's an exponential function along one direction and a sine function on the other direction. And right now here, this function is a sinh function on the x direction and a sine function on the y direction. So sinh is simply a linear combination of this exponential of x and the exponential of minus x. Now, again, what's left over is the exact value of this v naught. So we haven't applied the value of v naught yet, and say that that's the boundary. So when x equals b, sorry, I forgot to actually do a sum over n, and the complete expression should be a linear superposition of all this sinh kx and the sine ky, where this k is m pi over a, and the n is 1, 2, and now let's plug in the at x equals b, pi b over a sine k m pi over a, and this thing should be b naught because of the boundary condition over here. Now again, we try to determine what should be the value of the Cn. So the trick is the same, that we try to multiply this function we will try to multiply the v of y, the v of the function of y, by this additional integrate of sine km prime pi over a, and we copy the rest, which we sinh m pi b over a sine km pi over a, and this thing should be v naught, and the additional integral of and again, the trick is here this term can evaluate to be 0 when n is not n prime, and a over 2 when n equals n prime. So here this means it's Cn prime, and the sinh m pi b over a over 2 equals v naught integration of and we've evaluated the integral on the right before, should be 1 over n, and let's say the Cn should be 2 over a, and sinh m pi b over a, and here the integral on the right should be 2v naught a divided by m pi, and then the final expression of vxy should simply see by copying down the expression over here, and with the Cn plugged in, so it's 4v naught pi summation of all this odd n Okay, so this field of x or y should be now the complete result. So so this is all these examples for 2D Cartesian coordinates, and next we will go to 3D. And so, do you have any questions regarding this, the 2D separation of variables? If not, you can take a break, and we will continue the 3D discussion in the next session.